Electrophilic addition, the addition of an electrophile to an alkyne pi bond, is a very important reaction type for alkynes. In this video, we're going to look at general aspects of electrophilic additions to alkynes. The issues involved are essentially the same as those in alkene additions, but the structures involved are somewhat different. As in additions to alkenes, electrophilic additions to alkynes can involve two types of mechanisms, and the nature of the electrophile is really what determines what happens here. In a type 1 mechanism, the alkyne pi bond coordinates to E, the electrophile, and a leaving group potentially leaves. This generates a carbocation intermediate that may look a little bit odd in that the cationic carbon is sp hybridized and has a positive charge with one double bond and one single bond. It's what we call a vinyl cation or vinyl carbocation. Coordination of Y to the cationic carbon in an A sub n step then generates the product. This is what we call the type 1 mechanism of electrophilic addition. It's analogous to hydrohalogenation of an alkene, for example. In the type 2 mechanism, the electrophile rebounds in some way back onto the alkyne, forming a three-membered ring intermediate. And so while there is coordination of the electrophile to the alkyne through electron flow like this, at the same time, the electrophile rebounds back onto the alkyne, for example, through the involvement of a lone pair on the electrophilic atom. This forms a three-membered ring intermediate analogous to the halonium ions, for example, that we've seen, or a protonated epoxide that we've seen in an alkene context. In the second step of this mechanism, an SN2 type step takes place, where Y- attacks one of the electrophilic carbons, breaking one of the carbon E bonds. This type 2 mechanism is distinct from the type 1 mechanism in that it doesn't involve a discrete vinyl cation intermediate, and in that we would expect it to be anti-stereospecific since the stereochemistry of E and Y is set by this SN2 displacement step. Believe it or not, we see type 2 mechanisms showing up in some places for alkynes where alkenes react through a type 1 mechanism, the most important of these being hydrohalogenation, which we'll look at in the next video. As you've probably already guessed, electrophilic additions to alkynes can be subject to both site selectivity issues, and here the issue is primarily whether we observe the Markovnikov or anti-Markovnikov product, and stereoselectivity issues, and here primarily the question is syn versus anti. We'll only concern ourselves with site selectivity for terminal alkynes, which exhibit relatively clean selectivity due to readily understood mechanistic reasons. The issue with site selectivity is which atom forms a bond to E, the electrophile, and which atom forms a bond to Y. When a terminal alkyne reacts, there are two possibilities. Either the electrophile ends up connected to the less substituted position, and Y, the nucleophile, ends up connected to the more substituted position. Or the electrophile ends up connected to the more substituted position, and the nucleophile to the less substituted position. Thinking mechanistically here, we can reason that the first product is derived from reaction of this vinyl cation intermediate, while the second product is derived from reaction of this vinyl cation intermediate. Vinyl cations display the same stability trends that alkyl cations do, meaning that the more substituted vinyl cation, the one here shown in blue, is more stable than the less substituted vinyl cation. That makes the first product, highlighted in blue, the Markovnikov product, and the second product, highlighted in red, the anti-Markovnikov product. And as we've seen in an alkene context, we can't synthesize the anti-Markovnikov product through a vinyl cation. Reactions involving vinyl cations are preferentially going to give the Markovnikov product. But we can use strategies like hydroboration, where we've inverted the polarity of the reagent to achieve apparent anti-Markovnikov addition. Stereoselectivity issues are also important in reactions of alkynes. This tends to be a bit easier to think about visually than the alkene case since we're going from 1 to 2 dimensions. We don't really have to think in 3 dimensions. And we can make a direct parallel between syn addition to an alkyne and cis configuration in the product alkene between the added groups E and Y. We can also make a connection between anti-addition of the groups E and Y and trans geometry between these groups in the alkene product. When E and Y end up cis in the alkene product, we refer to this as syn addition. When E and Y end up trans in the alkene product, we refer to this as anti-addition. And stereoselectivity and specificity in additions to alkynes are very important, since we observe selectivity in some places where we wouldn't in additions to alkenes. For example, the hydrohalogenation of an alkyne, believe it or not, is actually stereospecifically anti. That gives us mechanistic insight, since additions involving alkenes are neither syn nor anti-stereospecific, this tells us that the mechanism of hydrohalogenation to an alkyne is fundamentally different from the mechanism of addition of HX to an alkene. We'll see more on this in the next video.